Today, we're exploring one of nature's most mesmerizing phenomena, fire. But we're not just talking about flames and heat. We're diving deep into the atomic dance that makes fire possible, how it connects to the sun, why trees exist, and how everything in nature is part of one beautiful cycle. This is Richard Feynman's explanation of fire, and it will change how you see every flame you ever encounter. But before we ignite this journey into the science of combustion, if you want to keep discovering the hidden connections in nature with me, hit that subscribe button right now for Discover Physics. Don't miss future videos where we reveal how the universe really works. And if this explanation sets your mind ablaze, give it a like to help more curious minds find these ideas. Now, let's understand why fire exists. Why does fire exist in the first place? Simple question to ask. You've witnessed fire 1,000 times throughout your life. Campfires burning bright, candles flickering, stoves heating food. You strike a match against the box, something ignites and burns, flames suddenly appear. But why does this happen? Most people never bother asking this question. Fire just exists as a fact. It's intensely hot. It's brilliantly bright. It destroys and consumes things. That's all you need to understand, correct? Incorrect. When you really dig into what fire actually is, when you examine what's genuinely happening when something burns, you discover something so beautiful, so perfectly interconnected to everything else in nature that it fundamentally changes how you perceive the world around you. Fire is not merely a thing that randomly happens. Fire is a window into understanding how atoms behave, how energy moves through systems, how the sun powers absolutely everything, and why trees exist in the first place. Allow me to show you this connection. Start with a piece of wood sitting somewhere. Dead tree material just sitting there doing absolutely nothing. And air surrounding it, oxygen molecules in the air floating around, also doing nothing in particular. The wood has been sitting in that spot. The oxygen has been there the entire time. Nothing's occurring. They're just existing together. But the atoms are attracted to each other to different degrees and intensities. Oxygen, for instance, in the atmospheric air would prefer to be positioned next to carbon atoms. And if they're getting sufficiently near each other, they snap together forcefully. But here's the fundamental problem with this. If they're not close enough, though, they repel each other and they separate apart. So they don't realize that they could snap together beneficially. This is the fundamental tension at the heart of combustion. Carbon atoms and oxygen atoms want desperately to be together. Being together releases energy, an enormous amount of energy. That's the stable state, the low energy configuration they prefer. But to reach that state, they have to first get close enough. And getting close means climbing over a barrier of activation energy. It's just as if you possessed a ball that was attempting to climb a steep hill and there was a deep hole it could fall into, like a volcano crater, a profoundly deep one. It's rolling along the surface. It doesn't descend down into the deep hole because if it starts to climb the hill, it rolls away again down the slope. But if you could make it go fast enough with sufficient velocity, it'll fall into the hole successfully. And so if you have something like wood material and oxygen molecules, there's carbon present in the wood from a tree that grew, and the oxygen comes and hits against the carbon, but not hot enough, not with enough energy. It just bounces away again, and the air molecules are always coming and bombarding. Nothing's happening at all. The atoms are bouncing off each other constantly and continuously, millions upon millions of collisions every single second, but they're not reacting chemically because they don't have enough energy. They hit, they bounce, they separate over and over repeatedly. The wood just sits there unchanged. The oxygen just floats around aimlessly. Nothing changes at all. This can continue on for years, decades, even centuries. A piece of wood material can sit in the presence of oxygen for 1,000 years and absolutely nothing happens. The atoms desperately want to react, but they can't get over that activation barrier. If you can get it moving faster by heating it up somehow, somehow, manage to get it started initially. A few of them come fast with high velocity. They go over the top of the barrier, so to speak. They come close enough to the carbon atoms and snap in violently, and that releases a lot of jiggling motion, which might hit some other atoms, making those go faster so they can climb up and bump against other carbon atoms. And they jiggle, and they make others jiggle, and you get a terrible catastrophe, which is one after the other, in rapid succession. All these things are going faster and faster and snapping in, and the whole thing is changing dramatically. That catastrophe is what we call a fire. It's just a way of looking at this process. And these things are happening rapidly. They perpetuate themselves. Once it gets started initially, it keeps on going continuously. The heat makes the other atoms capable of reacting to make more heat, to make other atoms react, and so on. This is the key to understanding fire fundamentally. It's not that something magical happens when you light a match. It's that you're giving a few atoms enough energy to get over that barrier initially. And once they do successfully, they release energy. That energy makes other atoms move faster. Those atoms get over the barrier. They release more energy. And so on in a chain. It's exponential growth in reactions. One reaction triggers two more. Two trigger 4 total. 4 trigger 8 altogether. The number of reacting atoms doubles and doubles and doubles within a fraction of a second. You have billions of atoms all snapping together simultaneously. That's why fire explodes into existence suddenly. It's not gradual or slow. It's sudden and dramatic, because it's a chain reaction, a runaway feedback process. So this terrible snapping is producing a lot of jiggling motion, and if I put with all that activity of the atoms there, and I position a cup of coffee over that mass of wood that's doing this, it's going to get a lot of jiggling transferred to it. So that's what the heat of the fire actually is. Heat is not a substance or thing. It's not a fluid that flows between objects. Heat is atomic motion fundamentally. The faster atoms jiggle, the hotter something becomes. When fire releases energy, that energy goes into making atoms move faster. That's heat. That's temperature. That's what you physically feel when you hold your hand near a flame. Fire is not a substance or material. It's not a thing you can hold. Fire is a process happening. It's this catastrophic chain reaction where atoms are snapping together faster and faster, releasing energy, making other atoms move faster, which makes more atoms snap together. It's a cascade effect. Once it gets started, it feeds on itself continuously. The heat from the reactions provides the energy needed to make more reactions happen. It's self-sustaining. That's why fire spreads outward. That's why it's hard to stop once started. The heat makes atoms jiggle fast enough to react. The reactions produce more heat. The more heat makes more atoms react around and around. A feedback loop perpetuating itself. And the only way to stop it is to break the loop somewhere. cool it down below the threshold temperature, remove the fuel source, remove the oxygen supply, cut off one leg of the triangle, and the process collapses completely. And then, of course, if you see, this is what happens when you just start to think deeply. You just go on and wonder, how did it get started? Why is it that the wood's been sitting around all this time with the oxygen all this time, and it didn't do this earlier? Where did I get this wood from? Well, it came from a tree, obviously, and the substance of a tree is primarily carbon. And where did that carbon come from originally? That comes from the air surrounding us. It's carbon dioxide from the atmospheric air. People look at trees and they think it comes out of the ground beneath, that plants grow out of the ground soil. But if you ask where the substance comes from, you find out where does it actually come from. The trees come out of the air. They surely come out of the ground, don't they? No, they come out of the air primarily. This is one of the most beautiful misunderstandings in all of nature. Everyone knows trees grow from the ground beneath them. You plant the seed in soil, the tree grows upward. Obviously, it came from the soil, correct? Wrong completely. The carbon dioxide in the atmospheric air goes into the tree and it changes it chemically, kicking out the oxygen molecule and pushing the oxygen away from the carbon and leaving the carbon substance combined with water. Water comes out of the ground, you see. But how did it get in there in the first place? It came out of the air, didn't it? It came down from the sky as rain. So in fact, most of a tree, almost all of the tree material, is out of the ground. I'm sorry, it's out of the air primarily. There's a little bit from the ground, some minerals and so forth. The minerals give you the ash when you burn wood material. That tiny bit of residue left behind afterward that came from the ground soil. But the wood itself, the bulk of the tree, the substance that burns, that's carbon from the air. That's water from the rain falling. Almost nothing came from the soil beneath. Now, let me prove it to you experimentally. Take a pot filled with soil. Weigh it carefully, plant the seed, water it for years. Let the tree grow big and heavy. Now dig up the tree and weigh the soil again carefully. The soil weighs almost the same as it did before initially, maybe a tiny bit less. Some minerals got absorbed by the roots, but the tree weighs hundreds of pounds more than it did as a seed. Where did all that mass come from? Not from the soil beneath. The soil didn't lose hundreds of pounds of mass, it came from the air surrounding it. This experiment has been done historically. The Dutch scientist Jan Baptist van Helmont performed it in the 1600s. He was trying to figure out where plant mass comes from. He weighed everything carefully and precisely. The soil barely changed weight at all. The tree gained enormous weight. He concluded correctly that the tree did not come from the soil, but he thought it came from the water alone. He was close to the truth. The water is part of it, certainly, but most of the mass is carbon pulled directly out of carbon dioxide in the atmospheric air. Now, of course, I told you, the oxygen and carbon stick together very tightly. How is it the tree is so smart as to manage to take the carbon dioxide molecule, which is the carbon and oxygen, nicely combined together, and undo that bond? So easily accomplished. Life has some mysterious force, perhaps? No, the sun is shining constantly, and it's the sunlight that comes down and knocks the oxygen away from the carbon atom. So it takes sunlight to get the plant to work properly, and so the sun all the time is doing the work of separating the oxygen away from the carbon. The oxygen is some kind of terrible byproduct which it spits back into the atmospheric air and leaving the carbon and water and stuff to make the substance of the tree structure. This is what makes life on Earth possible fundamentally. The sun is doing work, real physical work continuously. It's pumping energy into the system constantly. That energy gets used to push systems away from equilibrium, to create order out of disorder, to build structure. Trees are constantly doing this process, sucking in carbon dioxide, tearing it apart chemically, building themselves out of the carbon, releasing the oxygen back into the atmosphere. That's what photosynthesis actually is. It's the tree using energy to undo what fire does. Fire takes carbon and oxygen and snaps them together violently. Trees take carbon dioxide and rip it apart. The tree is using sunlight to do work, to store energy, to build structure. And that structure, that's potential energy stored. The carbon and oxygen are held apart forcefully. They want to be together, but they're separated. Energy is stored in that separation. And then when we take the substance of the tree and stick it in the fireplace, and there's all the oxygen made by these trees and all the carbon separated, they would much prefer to be close together again. And once you let the heat get it started initially, it continues and it makes an awful lot of activity while it's going back together again. And all this nice light and everything comes out and everything is being undone chemically. You're going back from carbon and oxygen separated back to carbon dioxide combined. And the light and heat that's coming out, that's the light and heat of the sun that went in originally. So it's sort of stored sun energy that's coming out when you burn a log. Think about that for a second carefully. The tree spent years collecting sunlight bit by bit, photon by photon, using that energy to pull carbon out of the air and build itself. It stored that energy in its structure. Then you cut down the tree, you let the wood dry, you stack it in your fireplace, and when you light it, all that stored sunlight comes pouring back out rapidly. The carbon that the tree worked so hard to separate from oxygen is collapsing back together. The energy that was stored is being released. Fire is just stored sunlight escaping. A log burning in your fireplace is the sun shining again. The light you see flickering in the flames, that's sunlight that fell on leaves 5 years ago, 10 years ago, 50 years ago, stored as chemical bonds, released all at once. Every photon from the fire is in a sense a recycled photon from the sun originally. The energy is the same. It went in as sunlight, got stored as structure, and comes back out as firelight. Now you might ask, why doesn't the wood just spontaneously catch fire by itself? If carbon and oxygen want to be together so badly, why do you need to light a match? Because of that hill I mentioned earlier, the activation energy barrier. At room temperature, the atoms aren't jiggling fast enough to get over the hill. They're bumping into each other constantly, but they're not reacting. The wood and the oxygen are stuck in what we call a metastable state. They want to react, but they can't get started. It's like a boulder balanced on top of a hill. It wants to roll down. That's the lower energy state. But it's sitting in a little depression at the top. It's stable as long as nothing pushes it. But if you give it just a little nudge, it rolls down and releases a lot of energy. That's what the match does. It provides the nudge. It heats up a small region of the wood, making those atoms jiggle faster, getting them over the activation barrier. Once a few reactions start, they produce enough heat to trigger more reactions, and the fire spreads. This is why things don't just spontaneously combust. The universe is full of metastable states, systems that want to release energy but can't get started. Wood and oxygen, gasoline and air, food and oxygen in your cells. They're all waiting for a trigger, a spark, an enzyme, something to get them over that initial barrier. And once they start, they run on their own. Here's another thing that should blow your mind. The oxygen in the air, where did that come from? From trees, from plants, from photosynthesis. For billions of years, plants have been ripping carbon dioxide apart, keeping the carbon and spitting out the oxygen. All the oxygen you breathe, all the oxygen in the atmosphere, it's waste. It's a byproduct. Plants don't want it. They throw it away. The early Earth had almost no free oxygen. The atmosphere was carbon dioxide, nitrogen, water vapor. Then photosynthetic organisms evolved. They started dumping oxygen into the atmosphere as waste. For them, oxygen was poison. Many of those early organisms died out when oxygen levels rose, but some organisms evolved to use that oxygen to burn food with it, to extract energy from it. And that oxygen is what makes fire possible. So here's the cycle. The sun shines. Plants use that sunlight to break apart carbon dioxide, building themselves out of carbon and releasing oxygen. Animals, including you, eat the plants or eat other animals that ate plants. And you burn that carbon, combining it back with oxygen to release energy. That burning happens inside your cells. It's called respiration. It's the same process as fire, just slower and more controlled. You're taking carbon-based molecules and combining them with oxygen to release energy. The carbon dioxide you exhale is the same carbon dioxide the plants absorbed. It's a cycle. Sun to plants to animals and back. Carbon circulating, oxygen circulating, energy flowing. Fire is just that cycle, sped up and visible. When you burn wood in a fireplace, you're doing exactly what your cells do when they burn sugar. Same reaction. Carbon plus oxygen makes carbon dioxide and releases energy. The only difference is speed and control. Your cells do it slowly, carefully, capturing the energy in useful molecules like ATP. Fire does it all at once, releasing the energy as heat and light. But it's the same chemistry, the same process. You are in a very real sense a slow fire burning. Let me make this even more concrete and clear. When you burn wood, you're converting chemical energy into heat and light. The chemical energy was stored in the bonds holding the wood's molecules together. Those bonds took energy to create. That was the sunlight the tree absorbed over years. Breaking the bonds and forming new bonds, carbon dioxide and water releases that energy back. The heat you feel, that's atoms jiggling faster, because energy was released. The light you see, that's atoms and molecules getting excited, literally electrons jumping to higher energy levels and then falling back down, emitting photons. When carbon and oxygen snap together, the energy released doesn't just disappear into nothing. It goes into motion. Atoms moving faster, molecules vibrating, electrons jumping to higher orbits. And when those electrons fall back down to lower levels, they emit light as photons. That's the glow of the fire you see. That's the flame itself. Different atoms emit different colors of light. Sodium produces yellow light. Copper produces green light. Strontium produces red light. That's why fireworks work with different colors. Different chemicals burn with different colors because they have different electron configurations. The smoke rising, that's tiny particles of carbon and other material that didn't fully react floating upward because they're hot and less dense than the surrounding air. The ash remaining, that's the minerals, the material that wasn't carbon, the bits that came from the soil originally, that's the tiny fraction of the tree that didn't come from the air. Everything else, the carbon, the hydrogen, the oxygen, has turned into gas form. Carbon dioxide and water vapor, invisible products floating away into the atmosphere. The mass didn't disappear mysteriously. It turned into gas and drifted off. Now here's the question you should be asking next. How is it the sun is so jiggly, so intensely hot? That's a different story entirely. I've got to stop somewhere in this explanation. I'll leave you something to imagine and wonder about. But before we end, let me tie this all together one more time. Fire is not magic. It's not mysterious. It's the universe doing what it always does, seeking the lowest energy state, releasing stored energy, transforming one form into another. Every time you see a flame, you're watching the sun's work being undone. You're seeing energy that was captured months or years or decades ago being released in seconds. The tree built itself from air and sunlight. Fire returns it to air, releasing the sunlight. It's a perfect cycle. And you, breathing in oxygen, burning food in your cells, exhaling carbon dioxide, you're part of that same cycle. You're doing the same chemistry that fire does, just slower, more controlled, more elegant. Fire is violent and fast. You are gentle and slow. But both are the same process at heart, taking carbon-rich molecules and combining them with oxygen to release the energy that the sun put in. The universe is full of these cycles, energy flowing from the sun, getting captured in chemical bonds, getting released again. Matter circulating, carbon, oxygen, water, moving from air to tree to fire to air again. Nothing is ever truly destroyed. It just changes form. The carbon atoms in the wood were once in the air as carbon dioxide. Before that, they might have been in another tree or in an animal or dissolved in the ocean. Those same atoms have been cycling through the Earth's biosphere for billions of years. They'll continue cycling long after we're gone. When you burn wood, you're participating in that ancient cycle. You're releasing energy, returning carbon to the air, continuing the flow that's been happening since life began on this planet. And that's beautiful. That's what Feynman wanted you to see. Not just what fire is, but how it connects to everything, how it reveals the fundamental processes of nature, how understanding one thing, really understanding it, opens up understanding of 1,000 other things. Fire teaches us about atoms and energy. It teaches us about the sun and photosynthesis. It teaches us about cycles and systems and how nothing in nature stands alone. Everything connects, everything flows, everything transforms. And when you truly understand fire, you don't just know why it's hot and bright. You understand how trees grow, how you breathe, how the sun powers the entire planet, and how energy moves through the living world. That's the beauty of physics. That's the beauty of really asking why, and following the answer wherever it leads.